Volcanoes are some of the most destructive natural phenomena on the planet, and they come in a variety of forms. This is Kilauea in Hawaii, an active volcano I've visited many times. Its current eruption has been going on since 1983, since when it's covered more than 100 square kilometres of land with lava.
I've been there too. I stood next to the lava flow, feeling the heat on my cheeks as it slowly made its way across the surface. It was absolutely fantastic. Kilauea is one type of volcano, a long, slow burner. But there are other types of eruption that are much more explosive, destroying whole mountains in seconds.
But as impressive as Earth's volcanoes are, they're nothing compared to what we see elsewhere in the solar system.
On this month's show, we bring you the most amazing and extreme volcanoes in the solar system. From the tallest to the coldest and the most dramatic.
We'll be using simple, Earth-based experiments to demonstrate the physics that drive different types of volcano. And trying to discover why volcanoes are so very different on different planets.
But let's start with the biggest. Here's geologist Hermione Coburn to explain why, impressive as Earth's volcanoes are, they are dwarfed by others in the solar system.
You might think that Britain isn't exactly overflowing with volcanoes, but Edinburgh here is built right on top of one. The castle over there perches on top of a plug of volcanic basalt. And this hill behind me, Arthur's Seat, that's another major part of the same volcanic system. It last erupted 340 million years ago. And this was a time before the dinosaurs. And back then, this area of Scotland lay close to the equator. And around here, you would have seen shallow seas surrounded by tropical swamps. And this dark rock, this basalt, would have been flowing out of the earth as molten lava. So this is how a volcano works on Earth. Heating within the planet melts rocks in the mantle. And those molten rocks, or magma, are lighter than the surrounding rocks. And so they rise up slowly towards the surface of the planet. And we can demonstrate that with this. This is a gelatin volcano. And it might look solid, but if I inject some molten rock or strawberry sauce, as I inject it, you can see that it seeks out cracks and fissures within the crust of the Earth. And it forms different shapes. If we get a vertical intrusion, it forms a dike. If it solidifies as a horizontal layer, we call that a sill. Sometimes you get a magma chamber building up. But some of the magma will keep rising towards the surface, and some of it will erupt out of the surface as lava running over the surface of the land in a volcanic eruption. And that's exactly what happened here at Arthur's Seat. Time and again, volcanic eruptions, lava spewed out of the volcano, building up the mountain behind us. Arthur's Seat is just a remnant of an ancient volcano, and what you're looking at is the exposed heart of that volcano that's been tilted and heavily eroded. It would have been much higher than it is now, probably about 500 meters higher than we can see here. But even then, that's tiny compared to other volcanoes. The largest volcanoes on Earth are the twin peaks of Mauna Loa and Mauna Kea on the biggest island of the Hawaiian chain of volcanoes. They stand over 4,000 meters above sea level. But if you measure from the seabed, from where they spring, they are almost 9 kilometers tall, taller than Mount Everest. But even the biggest volcanoes on Earth are dwarfed by the largest volcanoes in the solar system. The tallest volcanoes we know of are found on Mars. In the western hemisphere of the planet, we find the Tharsis Bulge, a vast area of high land dominated by 3 giant volcanoes, all of which would tower over Mauna Loa. And just to the north is Olympus Mons. At over 20 kilometers tall, it is the largest volcano in the solar system. To understand how the Martian volcanoes were able to get so much bigger than those on Earth, I've come to see volcanologist Lydia Hallis.
Lydia, tell me about the volcanoes that you get on Mars. Are they very different from what we find here on Earth?
Yes and no. The geology on Earth is really complicated compared to the geology on Mars, but we do get certain volcanoes on the Earth that are very similar to the volcanoes that are found on Mars. So these are some typical Hawaiian volcanic lava rocks that come from the top of Mauna Loa. And you can see some of them are really bright red colour.
I mean, that looks almost to me like you could have picked it up on Mars.
Yeah, some of them are bright red. Some of them that don't have oxidised iron inside them are a more green colour. And actually, when you scratch the surface of Mars, the red colour disappears and you're left with a green planet. So Mars is actually green.
So how do you know that?
We do have samples of Mars here on Earth in the form of meteorites. So this is a Martian meteorite. If we compare this to a sample of rock that came from the Earth's mantle, you can see it's quite a green colour, and it contains these minerals, olivine, which is green, and another one called pyroxene, which is also green, that contain unoxidised iron.
So chemically and physically, that's similar to what we find in the mantle on Earth.
It's almost exactly the same.
And yet, the volcanoes on Mars are so much bigger than those you get here on Earth. Why is that?
The difference is with plate tectonics. The Earth has plate tectonics, and Mars does not have any plate tectonics. So what that means is, with island chains such as Hawaii, you have a static plume of material that comes up from the mantle and erupts into a volcano, but the plate isn't static, it's constantly moving, so you get a chain of islands. On Mars, the crust itself doesn't move anywhere because there is no plate tectonics. So if you have a hot spot, it's constantly erupting in the same place, so the volcano just grows and grows and grows in the same place.
So that has just been continuously erupting and growing in the same spot for how long?
It's over 4 billion years that region has been active volcanically, and that's almost the same age as Mars itself.
So it's certainly one giant volcano. Is it still erupting? Is it active?
That's an interesting question. The youngest lava flows on the slopes of Olympus Mons are around 2 million years old. In geological terms, that's really young. So technically, Olympus Mons is still active, but there is no current volcanism.
When we look across the solar system, we see a huge range of different types of volcanoes. The volcanoes on Mars are different from those here on Earth, but they are also very similar. And that's because the processes of volcanism, the basic physics, is the same everywhere. And yet it can play out very differently depending on the local conditions that we find on other worlds.
Mars might have the tallest volcanoes in the solar system, but it doesn't have the most. That honour belongs to our other neighbour, Venus. The Centre for Planetary Sciences, part of University College London and Birkbeck, holds copies of almost all the images that spacecraft have captured of the planets. The surface of Venus is normally hidden from us, shrouded by the opaque clouds that form in its thick carbon dioxide-rich atmosphere. But we can use radar from spacecraft to map the surface, and these wonderful old prints from a spacecraft called Magellan are the result. And what they show are features like these: volcanoes, each of them perhaps 1.5 kilometers high and scattered across the surface. In fact, we think that Venus has more than 1,600 such large features. As well as these huge volcanoes, there are also tens, if not hundreds of thousands of smaller ones. But Venus also displays another type of volcanism, one not seen on any other planet. 2/3 of its surface is covered with lava flows, that aren't connected to the volcanoes, and Maggie has been finding out why.
Volcanic activity serves an important purpose. It's how planets lose the heat that builds up in their cores. The Earth loses most of its heat through the boundaries between its tectonic plates. But like Mars, Venus has no plate tectonics. That's one of the reasons it has so many volcanoes. But even they are not enough to release all the heat that builds up inside the planet. And that means the interior of Venus can overheat. I've been talking to planetary volcanologist Lionel Wilson to see how this relates to those huge lava flows.
Here we're looking at the other style of volcanism. There's a major fracture system like that off to the left of this image, and we've had sheets of lava coming out from the fracture.
I see, from a fracture, so not from a volcano now?
No, I mean, it's still volcanic, but instead of building up a pile all in one place, we've got a line source and we spread out sideways, so they look like this. And these are enormous. Some of these flows extend for as much as 700 kilometres, 400 miles.
There are vast flows like this over much of Venus. It's as if the whole planet has tried to turn itself inside out and poured its molten interior onto the surface. And it's all happened surprisingly recently.
What we see is that most of the surface is no older than something like 600 or 700 million years. One way of explaining what we see is that Venus builds up heat in its interior, can't get out easily again because of the lack of plates moving around, and so you then have an episode of violent outpouring of vast amounts of lava. So, you know, it gets through 300 million years worth of what it should do,
Yes.
perhaps in just a few hundred years.
Right.
And that resurfaces a large fraction of the planet.
We've long known that other planets had been volcanic at some point in their past, but the discovery of ongoing eruptions elsewhere in the solar system is actually surprisingly recent. Until 1979, the only place we'd found active volcanoes was here, on Earth. But then came one of the great discoveries of solar system exploration when Voyager 1 returned these images of Jupiter's moon, Io. It was a story that was recounted to the BBC TV series, The Planets.
Voyager took a few pictures, sailed past Io, and the scientists focused on Jupiter itself. Meanwhile, one of the engineers busied herself with some routine spacecraft maintenance.
The tape with the pictures the spacecraft had taken the day before was on my desk. I went and enhanced the brightness, and there appeared beside Io an object, a huge object that looked like something I could recognize and could never have expected, and it completely captured my attention. I wanted to know so badly what that was that I just had to ask myself, my goodness, what is that? And the answer that occurred to me first was it looked like another moon peeking out behind Io.
But there was no other moon, and no fault in the camera. Linda Hyder concluded that this object had to be part of Io.
And when I explored it, I was able to find that this large, strange object, it was exactly coincident and fell over a heart-shaped feature on Io. What I had discovered was the huge plume of a volcanic eruption rising 270 kilometers over the surface of Io and raining back down onto it. So I had discovered the first ever volcanic eruption ever seen on another world besides the Earth.
It soon became clear that the volcano that Linda Hyder had discovered was just one of many. Io turned out to be the most volcanically active body anywhere in the solar system. Its whole surface is coloured yellow by sulfur, and it's covered in volcanoes. The scars on its surface are in fact huge lava lakes, some hundreds of kilometers across, with a heat output greater than all of the volcanoes on Earth combined. Sometimes these lakes erupt, sending up volcanic plumes hundreds of kilometers above the moon's surface.
These giant plumes are caused by the same processes that power the most explosive eruptions on Earth. It's all down to how the gas dissolved in the magma beneath the volcano behaves when it reaches the surface. I've come to see planetary scientist Peter Grindrod, who has a very down-to-earth explanation for how this kind of explosive eruption works. So Pete, you're going to demonstrate to me a volcano. What are we going to use?
Okay, so we're going to do a classic experiment now. We're going to take some mints, we're going to drop them into cola, which is going to be our magma, and then we're going to hopefully see an explosive eruption.
So what do the mints represent?
Well, in this case, these represent the crystals that form in magmas. They act as a surface that the bubbles from the gas in the magma can actually start to nucleate onto.
Yeah, because the surface is quite rough.
Yes, so we need that roughness. The bubbles should form on the surface, and then that will act to disrupt the magma, forcing the volume up into the neck of the bottle of the volcano and erupt quite high.
How high are we talking?
We don't know yet. It's an experiment.
Let's find out.
There goes. And unlike real volcanoes, we probably know when this one's going to erupt.
Yes.
We're going to drop the mints in now.
Okay, that's pretty explosive, isn't it? That's quite impressive. It's going high.
That's really high. That's good.
I said this represents a volcano. What happens in both this experiment and an explosive eruption is that the large amount of gas dissolved in the liquid is released almost instantly, leading to a vast increase in volume. This creates an enormous pressure that can only be released in one direction, upwards.
This is a really good simulation of how we understand how volcanoes explode on the Earth. And interesting, it's also the process that drives some of the huge volcanic eruptions that we've seen on Io as well.
Those sort of plumes coming out into space.
We see them, yeah, plumes going really high, about 500 kilometers in some cases, up into space before raining back down in this really nice umbrella shape.
Well, who would have thought? Thank you very much. That's been wonderful.
The thing is, Io shouldn't be volcanic at all. It's far too small to have retained its internal heat from the time of its formation. But it's Jupiter's gravity that makes the difference. As the moon moves on its elliptical orbit, the gravity of the giant planet ebbs and flows, squeezing the heart of the moon, keeping it molten, and making Io the volcanic, active and dynamic world that we see. But Io is by no means the only moon in the solar system that's ever been volcanically active. There's another one, much closer to home. And that's what Pete's been looking at this month.
The moon's in a really good phase at the moment to see some very interesting features. Now, the region of interest is on the border between the lit and the unlit portion, because here, when you get raised features, they cast dramatic shadows across the lunar surface.
Looking at the face of the moon, we can see dark patches covering large swathes of the surface. These are the maria, Latin for seas, which early astronomers mistook them for.
Of course, we now know that these dark basins aren't actually filled with water at all, although naming them after seas has stuck as a rather nice idea. The dark material is actually solidified lava from ancient volcanic flows.
We can tell that lava flowed here fairly recently because we see far fewer craters in the maria than in the surrounding lunar highlands.
If you want to get in really close and see a lunar volcano, then you need to use, say, a 6-inch or larger telescope. Use the highest magnification you can that gives you a reasonably steady view, but if you push it too high, you won't see very much at all. This is the crater Keys, which is in Mare Nubium, the Sea of Clouds, very close to the centre of the moon's disk. Now, what's happened here is that basaltic lava has flowed in to Keys and it's flooded the crater floor.
The moon also has other, newer volcanic features. NASA's Lunar Reconnaissance Orbiter recently spent some time imaging this strange lumpy feature known as the Ina caldera. The level of cratering suggests it was formed by volcanic flows only 30 million years ago. The fact that this has happened so recently in solar system terms tells us that the moon may be cooling much slower than was previously thought. In fact, it may still be doing so. So what we're witnessing here is one of the last gasps of a once active world. There are other things to look out for in the skies this month, and one of the highlights will be the planets. On the 23rd, you've got Mercury, Venus, Mars, Jupiter and the Moon all together in the early morning sky, and that's what's known as a massing. And then on the 25th, you've got Venus and Jupiter really close together. For more details of this and other highlights in the sky this month, including the Orionid meteor shower on the 21st, consult my star guide on the Sky at Night website.
All the volcanoes we've looked at so far have involved lava, superheated molten rock. But that's not the only type of volcanism in the solar system. As we saw at the start of the programme, much more mundane substances like water and nitrogen can produce something almost counterintuitive, a cold volcano. When Voyager 2 flew past Neptune's moon Triton in 1989, it observed geysers of nitrogen gas and dust erupting kilometres above the surface. It introduced a new word to the language: cryovolcanism. But Triton isn't the only cryovolcanically active world that we know of. In 2005, the Cassini spacecraft discovered the so-called ice fountains erupting from the south pole of Saturn's moon Enceladus. Previously, Enceladus had been known for being the most reflective body in the solar system, reflecting 99% of the light that fell on it. But it is now revealing many more interesting secrets. Chris has been talking to Geraint Jones about this remarkable moon.
So when I think of volcanism and volcanoes, I think of hot things, and yet here we are in the outer solar system, and I think of large bodies, and yet this moon, Enceladus, is about the size of England, about 500 kilometres across. So what's going on? What activity could there be on this world?
On Earth, we're used to volcanoes being driven by magma, but as we move out through the solar system, further away from the sun, temperatures drop, and at these extremely low temperatures, water actually can take the place of rock. And all the features that we're seeing here on the surface of Enceladus are actually water ice. And we've got volcanoes as well, driven by water taking the place of lava.
And they were completely unexpected, I think, when Cassini got there, and yet there are these amazing images.
The discovery of active volcanism on Enceladus was one of the enormous discoveries of the Cassini mission.
And the pictures are great as
Fantastic,
well. That helps.
Yeah. When you see images of the plumes coming out of the South Pole here, they emerge in darkness and then they come into sunlight at higher levels. They're really beautiful sights. It's an amazing vista that Cassini's returned to us.
And so there must be water under the South Pole to fuel this activity. But what about the rest of the body? Is this just a local phenomenon?
Until recently, it was thought that maybe a relatively localized lake near the South Pole, but recently a more detailed study of the data that Cassini sent back strongly suggests that it's actually global. By looking closely at where the surface was during different Cassini encounters, they found that there was actually a bit of a wobble, suggesting that there was, in effect, some lubrication between the inner core of the moon and the icy crust, and so the fact that they weren't exactly tied closely together suggests that the icy crust is moving independently of the interior.
So there's some sloshing about which is affecting the surface.
Exactly, yeah.
So we now know that there's a liquid water ocean hidden under the ice of Enceladus. But how does it turn into these spectacular plumes shooting from the South Pole? So two questions. Why are we here, and why are you carrying a fire extinguisher?
Well, we're outside because this is the safest place to do this kind of demonstration, and I've got a fire extinguisher because it's actually quite a good analogy to what's going on at Enceladus. Because at Enceladus, under the icy crust, we've got liquid water under pressure. We've got the vents near the South Pole, and the water's escaping up through these vents. It's exposed to vacuum, and it turns to vapour as it's rushing up. And the fire extinguisher is quite similar, because in here at the bottom we've got liquid carbon dioxide. We release it, it's exposed, there's a big drop in pressure, and it turns to vapour.
OK, well, give it a go.
OK.
This is what an ice fountain looks like on Earth.
If you look quite closely, there's something else going on as well. As well as the vapour coming out, there are little solid particles of ice coming out as well. I'll just briefly show you that again.
Yes, look, here. Covered in snow. Right, OK, so I believe you. Solid particles. So what?
And the same thing happens at Enceladus. So we've got water vapour coming up through the vents. So most of it escaping out into space is in the form of water
Just the
vapour.
Yeah.
But we also have these icy water ice grains in the plume as well.
And that's crucial, because that's how we can see these plumes. Without the grains, without this process, we don't get these beautiful shots of the plumes of Enceladus.
That's right. It would be quite difficult to see without those solid ice grains in there as well, scattering sunlight.
On Enceladus, many of those ice crystals fall back onto the surface. And this is the reason why the moon is so bright and so reflective. It's constantly being covered with a fresh layer of snow. And the ice fountains do other wonderful things. Even more of the crystals spread around Saturn, forming one of its magnificent rings, the beautiful yet tenuous E-ring.
That's it for this month. Next month, we'll be casting our net beyond the solar system as we continue our search for extrasolar planets.
We have good evidence now for nearly 2,000 worlds around other stars. And who knows, by next month we might have our 2,000th discovery. And we'll be catching up with the search